Hello, respected selectors. This is Chinmoy Biswas, a recent graduate from the Department of EEE, BUET, recording a demo lecture for the position of lecturer in the Department of CSE, BRAC University. In this lecture, we'll talk about the electronic oscillators and its basic principles. The electronic oscillators are used in a wide range of applications, like in laptops and smartphone processors, for generating the clock signals, and in radio and mobile receivers for generating the local carrier frequency. An oscillator accepts the DC voltage and it generates a periodic AC signal of the frequency can even be a few hertz to a few gigahertz, with the output being either sinusoidal, rectangular, or sawtooth type. Schematically, the oscillator is nothing but an amplifier with a positive feedback. Now let's understand its working principle. Let's say some input signal is applied to this amplifier. So at the output, the input signal will be multiplied by the gain of this amplifier. So the output signal can be written as A times V in. Now let's say the output signal is given as an input to the feedback circuit. Now usually the feedback circuit can be modeled as a frequency selective circuit or a resonance circuit. And let's say the output of this feedback circuit is equal to Vf. So Vf can be written as beta times the output voltage, which is nothing but beta times A times the input voltage. And here beta is the feedback fraction. It basically means the portion of the output voltage that is given as a feedback to the input stage. Now, if the phase shift that is introduced by this amplifier and the feedback circuit is equal to 0, in that case, the feedback signal will be in phase with the input signal. Now, let's say this feedback signal is getting added to this input signal, and at the same time, the input signal is removed from the circuit. So now the feedback signal Vf will act as an input to this amplifier. So after removing the input voltage, whether we'll get a sustained oscillation or not, that depends on the product of A and beta. And this product is termed as the loop gain of the circuit. So if this loop gain A times beta is less than 1, in that case, over the period of time, the input signal will die out. And when, as we can see here, and when the loop gain is greater than 1, the oscillations in the circuit will build up. So in both cases, we are not getting a sustained oscillation. And sustained oscillation is only possible when the loop gain is equal to 1. So when A times beta is equal to 1, at the time, the feedback signal Vf will be the same as the input signal provided initially. And so the input signal and the feedback signal will be in the same phase. So in that case, we will get the sustained oscillation at the output. So in an oscillator, to get sustained oscillation, two conditions need to be satisfied. The first condition is that the magnitude of the product gain or loop gain should be equal to 1, and the overall phase shift that is introduced by the total circuit should be equal to 0. And these two criteria are known as the Barkhausen's criteria. And this criteria needs to be maintained for sustained oscillation. Now, so far, we have assumed that whenever this oscillator is switched on, at the time some finite amount of starting voltage is applied to this oscillator. But actually, if you see no signal, even if no signal is applied to this oscillator, but still we are getting sustained oscillation at the output. So the question arises, how is this possible? The answer is the thermal noise is always present in any circuit. And in a thermal noise, there is present all types of frequency components, starting from a few hertz to even a few gigahertz. So initially, whenever this oscillator is turned on, all the frequency components of this thermal noise will get amplified by the amplifier. And the amplified output of this thermal noise will be given to this feedback circuit. Now, as I said earlier, the feedback circuit is a frequency selective circuit. So out of all the frequency components, only one particular frequency, the frequency for which the phase shift that's introduced by this amplifier and the feedback circuit will be equal to 0, will sustain. And all the other frequency will have a different phase and will eventually die out. So from all other frequencies, only one particle frequency will be added to this input noise. Initially, in the oscillator circuit, the loop gain is set to be more than 1. And because of this noise signal of a particular frequency will get built up over time, and once the signal reaches to a particular input voltage, the loop gain of the circuit will become 1. And in this condition, the sustained oscillation will be maintained. And this behavior is possible because of the non-linear behavior of the amplifier or the feedback circuit. So in this way, the noise signal of a desired frequency will get built up over the period of time, and once the signal reaches particular voltage, then the loop gain of the circuit will become 1. So the sustained oscillation is maintained, and this is the basic principle of the oscillator. Now let's mathematically derive the Barkhausen criteria. Initially, let's say input signal Vin is applied. So at the first run, V out will be A times Vin. So when this V out is getting feedback, then the output of the feedback circuit will be VF. Then when BF will get added to V in, so V out can be written as A times V in plus VF. But VF can itself be written as beta times V out. So we get V out equals A times V in plus beta times V out. Now substituting, we get V out equals A times V in divided by 1 minus A beta. So we see sustained oscillation is maintained when this term is equal to 0. And this term is equal to 0 when the loop gain is equal to 1. And we can see here that as it is a complex quantity, we can write this as A beta magnitude equals 1, and the phase shift introduced by it equals 0. And we have seen here that we have proved the Barkhausen's criteria. So that's it for now. Thank you.